Hi everyone, and welcome to the Chapter 11 lecture, T-Tests for Related Samples. Previously, we've talked about single sample t-tests and independent sample t-tests. Now, we are going to discuss repeated measures t-tests. When we have a repeated measures design, also called a within subjects design, we have a single sample of individuals measured more than once on the same dependent variable. So instead of comparing two different groups of people, we are comparing people to themselves. Each person is used in all of the treatment conditions. So say you are testing a new medication for weight loss, hypothesized to have fewer side effects. You could assign people seeking to lose weight the original drug and then switch them to the new drug to see if those side effects disappear. So instead of comparing two entirely different groups of people who might experience the treatments differently, you can compare people to themselves. Here are some other examples. Maybe you're interested in whether a stats class increases stats knowledge. To test this, you give a class a stats exam on the very first day, just to see what they know, and then you compare it to how they perform on the final exam. Or maybe you're interested in treatments for depression. The image on the right shows a computerized brain scan before and after participants with major depressive disorder underwent what's called transcranial magnetic stimulation, or TMS, where magnetic pulses are directed at the brain. You can see that by comparison, that post-treatment, the brain had greater activity than at baseline before the treatment even happens. And you can see that in both of these examples, we aren't comparing two different groups of people, but rather people to their past selves. The equation for the related samples t-test is a little different than what we've seen before. In this equation, we have the sample mean difference minus the population mean difference divided by the estimated standard error for that sample mean difference. But before we can solve for t and find whether or not the difference is statistically significant, we have to solve for each part of the equation. To do this, we need to state the hypotheses and set the criteria as we have done before. But now we use the null hypothesis to find the population mean difference. Next, we need to find the sample mean difference. In repeated measures designs, we have what we call match scores, which means two scores for each person because they are measured at two time points. So we find the difference by subtracting score 2 from score 1, summing those differences, and dividing by n. Then we find the estimated standard error for the sample mean difference, and we can solve for t and then make a decision on whether or not it is significant using the t-table. Let's start with this example. A shoe company has developed a pair of tennis shoes hypothesized to improve running speed. To test this, the company samples a group of runners and has them run in both their old tennis shoes and the new tennis shoes for a given amount of time. The distance ran in that time is provided below. Is there a significant difference between shoe type? Step 1, we need to state the hypotheses and set the criteria. With related samples, we are hypothesizing about the difference between groups. And in this case, we are hypothesizing that the new shoes increase running speed. Because there is a specific directional hypothesis, we have a one-tailed test, and our null hypothesis is that mu equals 0. 0 meaning that there is no difference between groups. Our alternative hypothesis is that mu is greater than 0. Our degrees of freedom is just n minus 1, which is 3. So looking at the t-table, a one-tailed test with a p-value of 0.05 and 3 degrees of freedom means that our critical value is 2.353. From here, we can use the null hypothesis to identify the hypothesized mean difference. The null here is that the difference between populations is 0. Therefore, the population mean difference we are seeking for our equation is 0. As a side note, this number is almost always 0. The only time this number is not 0 is when a specific outcome is hypothesized. For instance, if we hypothesize a score will increase by 5 points, the hypothesized mean difference is 5. Next, we need to find the sample mean difference. We start by taking the mean difference, which is score 2 minus score 1. So 95 minus 100 is negative 5. 121 minus 100 is 21. 118 minus 95 is 23. And 123 minus 98 is 25. So then we sum those numbers. So negative 5 plus 21 plus 23 plus 25 is 64. And then we divide by n. So 64 divided by 4 is 16. Our mean difference is 16. Next, let's find the estimated standard error for the mean difference. We use the same formula for the estimated standard error as we did for the single sample t-test. If you need a refresher on this, you can see the Chapter 9 lecture, but I'll put the two variations of the equation here. While I tend to prefer the first equation, I'm going to be using the second equation with the sample standard deviation divided by the square root of n, just because the sample standard deviation is needed for finding the effect size later on. So let's start the process of finding the sample standard deviation. You can review the Chapter 4 lecture for a more in-depth explanation, but we are going to start with finding the sum of squares. Subtracting the mean difference from each score and then squaring it, we get 441, 25, 49, and 81, which total to 596. As a reminder, the sample variance equation is the sum of squares divided by n minus 1. So 596 divided by 3 is 198.667. Taking the square root of that, we get 14.095. So plugging that into the equation, 14.095 divided by the square root of 4 is 7.048. From here, we can solve for t. Here are those numbers we've identified for our equation from the previous slides. Bringing back up our t equation and plugging in those values, we get 16 minus 0 divided by 7.048, which is 2.270. This is less than our critical value of 2.353. So we fail to reject the null. There is no significant difference between shoe type and running speed. We don't typically report effect sizes for non-significant results because we can't really talk about practical effects if the effects themselves are not significant. However, I do want to show you how this is calculated. So to find Cohen's d for a related samples t-test, you divide the mean difference by the sample standard deviation. Pulling up both of those numbers, which we've calculated, we have 16 divided by 14.095, which equals 1.135. When looking at this table, which we've used before, this is a very large effect size. Here's a problem for you to try on your own. A school counselor is testing a new academic support program designed to change student test performance. 4 students volunteer to participate and take a standardized test before starting the program and then again after completing it. Did the program affect the test scores? Solve for T and Cohen's d. The answer will be shown in 5 seconds. Step 1, let's identify the hypotheses. This is a two-tailed test because we are only interested in whether or not a difference exists. The null hypothesis is that the difference between the population means is 0. The alternative is that the difference does not equal 0. The degrees of freedom is n minus 1, which is 3, and our p-value is 0.05. So using the t-table, our critical value is 3.182. Looking at this table on the screen, let's find our mean differences. Subtracting score 2 from score 1 for each individual, we get -4, 8, 2, and 10. which sum to 16. We divide that by our n, which gives us 4, and now we can find the sum of squares. Subtracting that mean difference from each individual different score and then squaring it, we get 64, 16, 4, and 36, which sum to 120. We can plug this into our sample variance equation, which gives us 120 divided by 3, which is 40. Taking the square root of that, our sample standard deviation is 6.325. And now we can solve for the estimated standard error. 6.325 divided by the square root of 4 is 3.163. And now we have all of the pieces for our t equation, which is 4 minus 0 divided by 3.163, and that gives us 1.265. But before we move on, we should solve for Cohen's d, which is the mean difference divided by the sample standard deviation. So 4 divided by 6.325 is 0.632. So what does this outcome mean? Well, 1.265 is less than 3.182. So we do fail to reject the null. There is no significant difference between the new academic support program and student test scores. Moving into test assumptions, there are two assumptions of related samples t-tests. First, the individual assumptions are independent of one another. This means that the people in the sample are not affected by one another. So in the shoe example, the participants are not competitors in a race trying to outrun each other. In the school example, these are not children who are working together to teach each other the material and boost their test scores. We want this information to be independent so that other variables are not affecting the data and changing the results. The second assumption is that the difference in scores is normally distributed. If the difference is skewed or there are extreme outliers, it can increase the chance of type 1 or type 2 error. Lastly, we should talk about advantages and disadvantages of repeated measures designs. One of the biggest advantages is that this design can examine individual changes over time. So instead of comparing two different groups of people, we can compare people to their past selves. And because we are using the same participants in both conditions, fewer subjects are needed, which reduces error due to individual differences. And it can also save time and money in terms of recruiting or paying participants for their time. However, time is also a disadvantage because if we are measuring people over a long period of time, that means we have to invite them back to the lab or wherever it is we're doing research. And over time, people tend to drop out of the study, especially if you're measuring over the course of months or years. And if the study is lasting that long, that is a long time to be collecting data. We also have to be aware of testing effects, where people may behave differently when given the same test at a different time point. For instance, if you're measuring stats knowledge and give the same exam twice, did the students actually learn the material, or do they just remember that specific set of problems? This is an issue with many different types of surveys, and it's just something to be aware of. And that is all I have for you. If you have any questions, please let me know.